Techlahoma is a volunteer nonprofit organization. So we've got 39 groups now, holy cow, 2 conferences, and we sponsor free local events like this one. You should check out our code of conduct to make sure that everything's above board. We've got a help wanted board at help-wanted.techlahoma.org. If you want to find ways to help us out and make our meetings have more impact. If you want to donate, go to techlahoma.org/donate, sign up for a monthly subscription. We are streaming live on Twitch. Hopefully it actually sounds okay right now. Cool, we're getting a thumbs up, so apparently we're doing something right again. And again, we're here at TBS today, and we thank them for use of their space. Again, Techlahoma is taking care of our pizza again today, so if you're not available to join us, we've got some pizza in the back, and thankfully, for whatever reason, since we're on Wednesdays, TBS has a food truck out back, so if you're getting kind of bored of pizza, and we have another one of these out here, you can come do that. So I'm going to let Jacob come up here and talk to us about reverse engineering Python, which is kind of an interesting topic. Apparently he had to do this for work, so here he is.
Thank you, guys. So I'm going to give a talk today about reverse engineering Python. This is something I actually had to do for work. A little bit about me first. I'm a DevOps engineer at Clever. Work mostly in cloudy stuff, AWS mostly. I'm a bit of a jack of all trades. I know many languages and not really an expert in any of them. I also have a shameless plug to my McSwain.dev site that I registered the day it came out. And then I've loved decompiling and reverse engineering things. It's always been a passion of mine. Probably stems from when I was younger. I used to take electronics apart, thinking that somehow I might be able to look at the PCB and figure out what's going on, even though I didn't even know anything about them. Sadly, I had this weird problem where 90% of the time they just didn't work after I took them apart. So I figured software is probably the better choice for me. A little bit harder to break when reverse engineering. The business case for this. So I was assigned a project with a process that was hard to work with. It was, you took a very organic input, a spreadsheet that was human-made, very hard to parse, and output a PDF that had to stay within a certain constraint. The existing solution worked, but it wasn't enough. They were still having to recreate their process or recreate these Excel spreadsheets manually every single time that existing solution failed. So they needed something better. This process was hard enough that it would take in just as much time to reverse engineer it as it would to re-implement it and potentially not give them the same level of compatibility they were already used to. We do know that they threw around the word Python a lot. They knew there was Python somehow, but what they provided us was a Windows executable file. So we figured it was probably PyInstaller or py2exe, one of the two. We didn't know what version of Python it was. We didn't know if they had been using this for 10 years or 1. And the previous developer went MIA. He wouldn't answer any emails or anything else like that. It just disappeared off the face of the earth. And the company does own the rights to this program, which is very notable, as we'll see in a second, because this does fall in a gray area. And I'm going to read this slide as printed here just to make sure that we're clear about it. This is pulled from the MIT's REC, which is the reverse engineering compiler. It was released some decades ago. There's a lot of discussion on the legality of decompilation. Decompiler tools have been available for a variety of platforms for a long time. Decompilers, along with other tools like debuggers, binary editors, disassemblers, etc., should only be used when the owner of a program has a legal right to reverse engineer the program. It has been established by the U.S. and other countries' courts that it is legal to use decompilers under the Fair Use Clause of copyright law, though note that you might be in a breach of contract should you use it, and it tells you not to, or license. And to find out when it is legal to use a decompiler, you should read the text of the following cases. Sega Enterprises Limited versus Accolade Inc. and Atari Games Corp. Versus Nintendo of America Incorporated. With that out of the way, one more note. This probably won't work well on alternative Python implementations such as PyPy, I guess that's how you say it, MicroPython, Jython, or any other interpreters that might output different bytecodes. This one works really well for the CPython, the standard Python interpreter that you will find. So a little bit of preface about how these executables work, py2exe and pyinstaller. I'm going to be mostly covering pyinstaller because that's where my experience is, but functionally they should be very similar once you end up opening them up and getting the compiled Python out. Py2exe creates a dist folder that has the DLL or the Windows library for the Python interpreter, and any accompanying code dependencies are in a library.zip file. It also has .pyd files, which are DLLs with native bindings to Windows libraries, and DLLs that are purely native to Windows. pyinstaller does nearly the same thing, but instead it packs it all into the single binary executable. Compiling Python. So Python is interpreted, but it's also kind of compiled. Whenever you import a library of Python, and if it's from source, it will take the time to compile it to bytecode right then and there. A bytecode implementation helps with the next time you go to import it. It should hopefully be a little bit faster, potentially magnitudes faster. It's similar to the way the JVM works. Java recently allows you to actually run the source interpreted, but it will make a bytecode output as well. There's actually the PVM, which is a Python virtual machine as well. Of course, to do any of the examples in this presentation, you'll need a PyC file to work with. Python does compile when you import it or run it, and if it does not for some reason, if you're running it directly, you can use python-m pycompile to load the pycompile module and compile the file that you're pointing to. If you're on Python 2, it'll make the PyC file in the same directory as the source code you ran, or if you're in Python 3, it'll make the __pycache __file .cpython-3.7 or whatever version .pyc. And you actually can run PyC files directly. You can run Python and the path to the PyC file, and it will run it just the same. As far as options go for taking PyC, compiled Python bytecode, and bringing it out back to Python source, there are a ton of toolings actually. One of the leading ones are the uncompile line and the decompile. Uncompile 2 came around real early. It's slightly maintained now as there's no new revisions coming out of Python 2, and it only works for Python 2. It's an almost near perfect implementation of the bytecode, re-implementation of bringing the bytecode back to Python. Uncompile 6 works on Python 1.3 to 3.7. It does have many issues because some of these versions of Python are being updated every single day, and bytecodes change all the time with the version 3 of Python. It's the spiritual successor to Uncompile 2. It's not written by the same person or anything else like that. And there's also Decompile 3, which is made by the same person as Uncompile 6 that targeted Python 3.7 only and re-implemented it to hopefully avoid long-standing bugs and existing problems that have been in there for a long time. There's unpyc3, which is unmaintained. It was really good for Python 3.2 only. And then another one of note is unpyc 3.37, which is a fork of unpyc3 for Python 3.7 only. You'll notice here that a ton of these are forks of forks, and the ecosystem for this is kind of spread all around. If at this point, when I was looking in how to do this, if I were to Google search Python decompilers, every single link on there is purple now because there's so many options. So PyC to assembly options. You actually can get an assembly version of Python out of the PyC files. There's dis, which is the built-in disassembler, xdis, which is a drop-in replacement for it from the person who made Uncompile 6, and then XASM, which is the complement to xdis, which assembles Python disassembly. It does not work for Python 3.6, but as of 2 months ago, support for Python 3.6, 7, and 8 were added, but it's still not pushed to pip yet. You'd have to grab that from GitHub. Uncompile 6, 2, and decompile 3. These are functionally the same and have very similar APIs. They're most useful with CLI tools. You should use the same version of Python code as you're trying to decompile because it will pull the opcodes from your running implementation. And then again, Uncompiled 2 is a near perfect implementation because it's not being maintained. Python 3 is more difficult to work with as there are a lot of changes introduced with each version. And the biggest problem I had with Uncompile was there's a binary output, meaning it either fully decompiles or it does not decompile at all. You don't have partial decompilation. But at this point in time, it is pretty much the de facto standard for decompilation. Okay.
Would the PyC bytecode be different on Windows and on Mac?
No, it would not, because the bytecode. Oh, so the question was: is the PyC bytecode, would it be different between different operating systems like Windows or Mac? And the answer is no, because the bytecode isn't run on native as a native language. It's still interpreted by the Python interpreter. It's just a little more efficient. Uncompile works like a compiler. It's pretty interesting. Everything else looks at the bytecode kind of line by line and makes a resulting function call or the code from it. Uncompile works like a compiler, whereas it will lex things. I'm actually going to read this from the Uncompile README because it does itself some justice. And do note that it's a little self-congratulating here, but it's true. Using compiler ideals, the program creates a parse tree of the program from the instructions. Nodes are at the upper levels that look a little like what might come from an abstract syntax tree in Python. So we can really classify and understand what's going on in sections of Python bytecode. So it looks at it as sections instead of individual lines or individual instructions to hopefully understand a better idea of what's going on with logic flows and such. Building on this, another thing that makes this different from other CPython bytecode decompilers is the ability to parse just fragments of the source code and give source code information around a given bytecode offset, which I just covered. Python fragment deparsing given an instruction offset is useful in showing stack traces and can be incorporated into any program that wants to show the location in more detail than just a line number at runtime. So when you get a stack trace, it kind of does the same thing. It knows what the stack looks like and where it's been run. It gives you a little more context than just error on this line. His debuggers also make use of that. There were and still are a number of decompile and compile and so on forks around. Almost all of them come from the same code base, and almost all of them are no longer actively maintained. This was a big issue, and he took all these forks and tried to bring them all into one project and move that going forward, which is why it has the most compatibility and is the de facto standard, working from 1.3 to 3.7 plus. So that's a little bit about Uncompile and why it's so noteworthy. And a little bit more about the modern versions. They work hand in hand with xdis and XASM. They do have problems with some newer features like annotations and things that are really recent and don't matter as much and aren't used as much. If it's a popular bytecode that's being used, it will have precedence and priority to implement the reversing of that versus something like annotations, which are hardly used. The CLI is fairly simple. You run uncompile 6, -- verify, runs it through the interpreter afterwards to make sure it makes logical sense. The -o option's your output, and then the last positional argument is the path to the compiled binary. So extracting the exe. I actually do have some live demo-ish things without the live part using a cinema. Whoops. So decompiling or extracting the executable. As you'll see here, this is using a cinema, which I really like. It takes the live out of live demos, but gives you the same kind of experience. Basically, this is using python-exe unpacker, which works with py2exe and pyinstaller. And it will unpack it, grab any files out of it, and give you the PyC files that are inside of it. And you'll see here, I'm running the pyinstaller extractor on the binary. It processes it. It shows that it's pyinstaller version 2.1 or above. It's Python version 3.7. The size of the package, how many files are in there. The PyZ archive is that library.zip that I mentioned earlier that has all the libraries and your source code inside of it. You'll see here that I'm going to list what's in there. There's a base64.py in there that's been packed in there. And I'm going to open hex edit on there. And this is pretty notable. The bytecode on here is very important. PyInstaller has this weird thing where it likes to mangle the magic value of the PyC file when it gets incorporated into the executable. Not sure why, I'm not sure how that would even work, but it does. Do take note of the position of the E30000 address or code, binary hex, whatever. Sorry. And you notice that it's 4, I guess these are 8 bytes in. And you'll see that basically where the values don't add up, we'll just be taking it. It's the PyC file from the base here is from the PyInstaller extractor. It uses the same version of Python as the target code we saw in the exe unpacker that was Python 3.7. And I ran the PyInstaller extractor with 3.7. So the magic value should match very closely. Everything up to the E300 and so on. And so basically I'm going and making those match by manually hex editing it. And then I'll be saving that. And moving on to the next step. So the magic. What's actually in a PyC file? This is a bit outdated because Python 3 has changed the way the magic works several times already. But the theory is still the same. It's a way to identify which version of the bytecode that is being ran or that you should run against. It has a 4-byte modification timestamp to show the last modification date, and a marshaled code object, meaning it's the code object's packed into the file. So I have another demo of decompile working. I was trying to avoid technical issues, but that didn't work so well. This is me using uncompile 6 on the binary from the that I just edited and changed the magic value to match with. You'll see that it executed perfectly fine, it verified, and outputted the file in base64.py. And I'm actually going to run it. I believe it's a standard library because it does have a CLI interface, but it could be a third-party thing that was in there. I basically encoded with it, and I'm going to decode that same string back out, which should be test. There we go, and I'm going to cat the message as well just to verify that's actually what was put in there. That was the best case scenario. Doesn't always work like that, and that's the real meat of the talk, is when it does not work. If it fails, it's a lot more angry. So you'll see here, we'll be running it on a bytecode that was from the application I was going to decompile. I'm not going to be outputting the source code or anything here because it is copyrighted. But you'll see that there's, it's a huge stack trace that ends up getting printed out, and then a very useless error message that says parse error near the none instruction at offset -1, which really doesn't tell you anything. If you actually scroll up through the log and find the none value anywhere in that stack trace that tells you, nothing is invalid at all. And so that's where the problem runs in, where it's very binary. You either get output or you don't. You can't pass over instructions that are invalid. That's where other projects come in, like unpyc 3.7. It does not also allow you to do partial, but it gives you a cleaner error message out of it. So if I run that same file through unpyc 3.7, you'll see that it actually errors on the bytecode setup annotations. Again, this is a very new Python feature added in 3.6, and there hasn't been any support added for it. Oddly enough, the developer for this used annotations, so what to do from here? That looks more like a code error, like something you'd see in your day-to-day life. Why wouldn't we just implement that? So we go to implement it. You can add this line right here and make it a no-op. Set up annotations, as we'll find out later in the dist documentation that shows you the bytecode, is works internally on the stack and does not, you can't write a piece of code or a line to call that. It's implied. So it doesn't need to output anything with that instruction. So we can just make it a no-op and just return. I actually made a pull request to add it to the project that got merged in this morning at 11:25. So fun for that. And then we have output now. So running again with that change in place, we're going to pipe it out to trouble.py. And note that I'm not going to cat it here. I'm going to count the number of lines, and we get a 1,000-line file out of it. Yeah.
Switch question.
Okay.
If you structure code in such a way as to make it difficult to compile?
Okay, so the question was, could I structure a code in a way that makes it difficult to decompile? I actually am going to talk about that towards the end of the talk. I have ways to protect yourself against this. So yeah, we have output now. So a little bit about xdis. Xdis can be used as drop-in replacement for dis. Dis is the disassembler built into Python. Have an example of disassembling it here. So have a test program. Oh, I disassembled the python-exe-extractor, which doesn't make for a good demo. But xdis prefers you to have a .py-asm file to work with the assembler as well. Of course, it got the bytecode out properly. And funnily enough, that first line here is a doc string. It actually does preserve doc strings in the binaries. So interesting note, it does preserve variable names as well. So if you decompile it, you're not going to have mangled variable names. You're going to have what were actually written. And then opcodes can be found and diagnosed or figured out what they mean here in the dis library. For example, setup annotations. Here, checks whether the annotations is defined in locals. If it's not, do whatever it needs to do, and it's new in Python 3.6. XASM. It's an assembler for xdis. It's useful for changing the behavior, removing troublesome opcodes like setup annotations. Sadly, I could not get it working with Python 3.7, though it looks like they did add support for that recently. But I do have a demo of it with a much simpler program. So you can see the function, or the program there just has a function called 5 that returns 5, and it prints the value of the 5 function being ran. Using Python 2 here because I wanted to make sure that it actually worked. I'm using the py disassemble binary that or script that comes with xdis, using the --asm option, which will put it in a format that XASM can use. You bring it positional argument, the binary you want to use, and then you pipe it to text.pyasm or test. And you'll see if we edit it, that's what the bytecode looks like. I'm going to edit it here. I don't know why, but the first line had this issue where it was trying to put the current path. But I edited 5 to 10 here. And I'm going to be using XASM to reassemble this file and run it. Now you'll see here it has an XASM CLI, and you pass it the PyAssembly file. And it will write the compiled binary. And running that directly should output 10 instead of 5. And it did. And then I'm just going to run the original program just to show that it is a different behavior. So looking a little bit closer at the assembly code, the actual code's written here on the screen. You'll see I put the PyC file down at the bottom just to show that you really can't get any truly valuable information by outputting it directly. Figured why not. The PyAssembly here. So this is the actual full output of the PyAssembly without the comments added by xdis. You'll see here the two, I'm going to exit out, that way I can use my pointer. Okay, so you'll see the 2 here refers to this is running on line 2 in the source code. It loads the constant 5 onto the stack, and it returns that value. 1 refers to the line, and the first line was defining the function 5, as you recall, here. So we'll load that code object from memory, make a function out of it, and store it in the name 5. And then on line 4, which is the executing it and printing 5, it loads the item 5 from the heap, calls the function with no arguments, prints the item, prints a new line, loads the constant, and returns the value. I want to dig a little bit deeper about what these actually mean, these bytecode or opcodes actually mean. Load const will load a constant into the stack. So in this case, it's the literal representation of 5. It will load that onto the top of the stack, and return value will actually return the top of the stack out to its calling function. So it returns top of the stack to the caller of the function. On line 1, load const will load that code object, make a function out of it. Make function's interesting because it's used very sparingly here. There's no arguments to make a function out of or anything else like that. But that first argument that's a 0 now could be any kind of bitwise operation of these that say it might need a tuple inside of it, it might need an annotation, and so on. But in this case, it's the most simple version of it, no special arguments or anything else like that. And then it stores that function that's been created on the stack with this in the name 5 and puts that on a heap. And then on the last part is a lot more fun. So it loads the name 5 from the heap, which refers to the last slide we looked at that created that function. And it calls it with zero positional arguments and no keyword pairs or anything else like that. Just calls it straight up. Print item is actually not defined as a proper bytecode, but it's one of those that's easy enough to understand what it does. It prints the top of the stack. And then print new line, obvious as well. Then it loads the constant none and returns that. So this is interesting because if you're a native programmer like C, you might have seen before when you have a function that does not return anything, it's void, and you can actually return, just use a return statement, and it's valid. This kind of does the same thing. You don't have a return value, so you're explicitly saying you don't have one. Call functions, interesting as well. To make short of this, basically call function pops all the arguments and callable object off the stack, runs the code upon that, and a return value is put on the top of the stack. So thus you can call the function, your output of the function, which is 5 in this case, goes to the top of the stack, you print the top of the stack, you print a new line, you load none to the top of the stack and return that. That's the basic building blocks of all PyAssembly, and you could take this if a decompiler does not work for you in any case or something's unimplemented. You could go in, look at the documentation, and piece together what an area is working with. If there is a way to get partial decompilation out too, that'd be even better, because you could complement that with, instead of having to go through a 1,000-line file to figure out what the whole thing does, if one function fails, you can go through, disassemble that one by hand, and everything else be automated. So protecting yourself from reverse engineering. So this part's very interesting. Back out to presenter mode here. You have a couple options for protecting yourself from this. One is obfuscating your code. Another one is using Python. PyInstaller has an encryption option and SAS. So obfuscation, do note that it's not security. It makes it harder to decompile, but it's not impossible. PyArmor is probably the best choice, and note that I haven't evaluated any of these. I did a quick search for the popular ones. PyArmor looks like it's probably the best choice. It's very popular. Not only does it allow you to obfuscate code, it allows you to lock a certain binary to a certain machine, and also gives you the ability to, after a certain amount of time, make that script unexecutable. Not sure exactly the details on implementation, but that's something I'm actually going to look into in the future. You have PyMinifier, which is just a simple minifier and obfuscates variable names and function calls and so on. And OPy is basically the same way. It's also semi-popular. And Python can do obfuscation, but not in the same way. It doesn't mangle variable names. Python's a way to convert your Python code to C and then out to machine code. It's still able to be reverse engineered, but it'd be much harder to get working Python out of it due to the fact that you're going down 2 stages. It'd be much harder to go up 2 stages back to Python. But you might get working C code out of a Python binary at that point. It could be worse because C decompilers are very mature. C's been around since the 70s, and decompilers and everything else like that just as long. So that potentially might not be a great option. It really depends on your use case. PyInstaller has an encryption library or encryption option as well. You can use AES 256 to obfuscate your code. I'm not sure the details of that, but even on their README that talks about that, they say it's still easy to decompile the binary and get the key from it, and you have all the code. Just as an extra step, maybe makes it a little harder, or maybe some people aren't as motivated. We'll stop at that point. Really depends. If you're a target, you're a target, and you know you're going to need to go as far as you can. And one of the last ones is using a SAS. Make the code execute as a SAS, software as a service. You can hide the execution behind HTTP request. I mean, honestly, you can't decompile the code if you never have it. But in the same vein, this is probably not the best option for most cases because there's no need for a cloud-native distributed containerized RESTful microservice based on ARM v7 with Kubernetes Hello World as a service. Sometimes your program just does not work as a software as a service. Sometimes you just have to release it. And in conclusion with that, as far as protecting yourself, you can't. Any code that can be executed can be decompiled. It might take years, it might take decades, or it might take minutes. If the code can be executed at some point in the call stack, it is running in its pure form, and you can reverse engineer it. Your best bet, if you're really trying to be secure, is to make it as difficult as possible. And with that, Q&A. If anybody has any questions, I'll be glad to answer them now. Yes, the project was a success. We managed to take a executable, Windows executable, and make it an AWS Lambda. And now, given email inputs, it runs and outputs to an S3 bucket. So we're able to do a couple of bug fixes on it as well. All right, well, that's it. Thank you guys so much.
So if this didn't blow your minds already, like I've watched a couple of talks where they've talked about actually writing code to change the bytecode in the currently running interpreter, and it's really like messes with my head. But back in the python-exe channel on May 8th, Jed posted a link that he thought I would like. It's from anvilventures.com. And it's a link entitled "Looking Inside the Box." It's somebody literally doing this to Dropbox because their entire app is in Python. So you should take a look at that blog entry if this is interesting to you and is really cool. Do we have? Can Python be written with Unicode variables? I honestly don't know. I know that you can do that in JavaScript where you can use emoji as your variable names, but I don't know if you can do that in Python 3. I know you can't do it in 2.7. Like maybe. I feel like you probably shouldn't. Like that seems bad. Oh wow. So Test Suite uses Dropbox source code to make sure that's working. So yeah. So anyway, another word from our host.
Yeah. We had some audio issues earlier, so I was not able to be heard. Just wanted to remind everybody out there that might not be available at the beginning that we, TBS, have this event space open, and it's available for people that are interested. There's some information on our end. Reach out on Slack or Techlahoma and then get a hold of me. We'll get that to you. Again, this is TBS, as you can see all around behind me, and We are a 51-year-old company that does financial services for small businesses. So if you have a small business and you have any interest in finding out about our services, please reach out. Thank you all, and have a great one.